Hello everyone, in this segment we are going to talk about the moment of inertia for a triangle. A triangle having base B and height equal to h, and with x and y axes are intersecting on the left hand corner. The triangle ABC can be considered as composed of two right angle triangles when we are dropping perpendicular from point C to line AB. The point of intersection will be considered as D. The distance AD will be let equal to A, while the remaining portion from length GB will be equal to B minus A. If we consider this triangle ABC as composed of two triangles, the first triangle, right angle triangle, is ADC, and the x-axis and y-axis are intersecting at point A. This triangle, we call it triangle number 1, having base equal to A, which can be considered as it is the case number 2. While for the other triangle, triangle number 2, which is DBC, this is 90 degree, the base equal to B minus A, and the height is equal to h. But regarding the y-axis, we will find that this y-axis having distance equal to A from the side DC, and we can call this right angle as case number 1. In order to estimate the moment of inertia at the x direction, we are going to write down all the expression which we have obtained previously. That for triangle number 1, we have ix1 equal to the base multiplied by the height raised to the power of 3 divided by 12. Our base is A and our height is h. So we have ix for the first triangle is equal to AH cubed divided by 12, while for the second triangle, the expression is ix2 equal to the base also multiplied by height raised to the power of 3 divided by 12. But in our case, since the base is different length, it's equal to B minus A. Then the ix will be B minus A multiplied by h cubed divided by 12. We are going to sum these two values together in order to get the ix value for our original triangle ABC. We'll move to the next slide. So ix final equal to ix1 plus ix2. So we have AH cubed over 12 plus B minus AH cubed over 12, taking 1 over 12 H cubed as a common factor, and we open one bracket. Inside the bracket we have A plus B minus A. So A will go with minus A. We are left with H cubed B divided by the 12. Since the area of that triangle is 1/2 BH, then we can get the radius of gyration by the expression k squared x equal to the moment of inertia of the final value for the triangle divided by the area, which is h cubed b divided by 12, all divided by 1/2 bh. So we get the expression of h squared divided by 6 as the k squared of x. In order to get the expression for the moment of inertia as a CG, first we have to find out what is the distance y bar of the CG in order to apply the parallel axis theorem. So we'll move to our third slide. In order to get the y bar, we have the law that ay bar equal to the summation of a I yi from I equal to 1 to I equal to 2. So we have a1 y1 plus a2 y2. The big area is 1/2 BH, multiplied by the height y bar, which we are looking to for getting the expression of that value. The first triangle is 1/2 AH, and the CG y1 equal to the h over 3, plus the second triangle, which is 1/2 b minus a as a base multiplied by h, and the y2 equal to also 1/3 of h. So on the left hand side we have 1/2 bh y bar equal to, our common values are 1/2, and we have here h squared and also 3. We open one bracket. Inside that bracket we have a plus b minus a. So we get h squared b over 6. We have here bh and we have here bh squared. So we left, and we have here 6 and we have here 2. So our y bar equal to 1/3 of h. We will proceed to get the moment of inertia for the ix. Then the ixcg, using from the parallel axis theorem, we have already obtained the ix for the big triangle, which was bh cubed divided by 12. We are going to subtract the multiplication of the area by the y squared value, which we have just obtained, which is, the first bracket is 1/2 bh multiplied by h over 3 raised to the power of 2. We have bh cubed over 12 as a common factor. We open one bracket, we have 1 minus, here we have h squared over 9 multiplied by 2 becoming 18. So we have inside the bracket 1 minus 12 divided by 18, which will leave us with 6 over 18 bh cubed divided by 12. So we have at the end that ix at the CG bh cubed divided by 36. In order to get the radius of gyration, the k squared x equal to the moment of inertia at the CG divided by the area. We have bh cubed over 36 divided by the area, which is 1/2 b multiplied by h. So we will have k squared x equal to h squared divided by 18. Next lecture, we are going to find out the moment of inertia at the y direction for the triangle. Thanks a lot and see you. Goodbye.